Today I'm going to talk about our work on verification for cluster management, the system Kivi. This is joint work with Gangmuk, Ryan, and Brighten. So how are cloud managed? They are powered by the cluster management system like Kubernetes, Docker Swarm, AWS ECS, and they consist of this multiple automatic controller that continuously monitor and drive the infrastructure towards the desired states. So this picture illustrates how a controller works. So it's receiving these high-level policies and then collecting metrics from the underlying system and then deploy their actions. You can see it's forming this closed-loop dynamic decisions. So one example is the scheduler that's trying to schedule replicas onto node according to some user-defined policies. So how could things go wrong? We studied hundreds of failure reports collected by communities and also GitHub issues. There are many different kind of issues like DNS issues, Linux kernel issues, configuration syntax problems. So among all these issues, we identified a failure pattern that hasn't been discussed sufficiently before, which is caused by the non-trivial interactions between controller configurations or between controllers and events. So events here can including things like node failures or maintenance. This is really because there is no global coordinations between those controllers. So each control components may have their own goals. They also may be designed by separately. However, they may have the shared dependencies. And they're also possibly configured by different teams, may have different objectives in mind. So next, I'm going to give you a motivating example about how things can actually go wrong. But before, so quickly show you how these non-trivial interactions may actually look like. So from left-hand side are the controllers, so they are interacting with each other as well as with the environmental event on the right-hand side by manipulating the system state in the middle, which the system states are the shared dependencies. So before we look into the motivating example, let's first talk, just briefly mention what are the terminologies for Kubernetes. So Kubernetes is the most popular open source cluster management platform in cloud computing, and pods are the smallest deployable unions that consist of containers. And deployments specify and store information about life cycle of a group of pod. And nodes are the virtual machine or physical machine that actually runs the pod. There are some famous controllers like deployment controller trying to maintain certain number of pods. There are the horizontal pod autoscaler trying to scale up or scale down the number of pods according to, say, resource usage. There are also schedulers and deschedulers trying to schedule or evict a pod according to some user-defined policies. So let's look into one real-world example caused by this non-trivial interactions between controllers. There are 3 nodes. Each node is showing at the box here, and they're divided into 2 groups. The on-demand group has 2 nodes, and the spot group has 1 node. There are 3 controllers involved in this case. So the deployment is trying to maintain 10 pods in total. And the scheduler has been configured with a topology spread constraint that trying to evenly balance the pod across the 2 groups with a maximum skew of less or equal than 1. The skew here means the difference between the total number of pods across the 2 groups. There's another plugin has been configured called node affinity that trying to prefer the on-demand node over the spot node, with the higher weight for the on-demand node. So you may notice that these 2 policies actually conflict to each other because the topology spread is trying to evenly balance the pod across the 2 groups, while the node affinity is trying to prefer some node over another one. But they're OK so far because the user has configured them into a soft constraint. So the 10 pod can actually be scheduled as shown in this figure that you can see that right now this on-demand group has a total of 6 pods, while this spot has 4 pods. The difference now is actually 2 pods that is more than the 1. So that's saying the topology spread constraint is actually violated. But it's still OK because those are soft constraints. However, things can go wrong when you have a descheduler is configured with removing the pod that violating this topology spread constraint. So with this config, the descheduler is going to evict the pod on this on-demand group because it have one more, it have 2 skewer. So, and then because the deployment controller needs to maintain 10 pods in total, so a new pod will be recreated and then will be rescheduled by the scheduler onto the same node again, and will then be evicted by the disk scheduler again, so on and so forth, that causing these oscillations, that the pod will be in this unending circle of scheduling and eviction. So this is really caused by a descheduler logic bug we found, plus the descheduler should be configured not to evict the pod according to the soft constraint. I also want to briefly mention that even correctly using a single controller is actually hard. So this shows a framework for the scheduler where it contains 12 pipeline stages in total, and there is 21 default plugins. And even for a single plugin, the topology spread constraint, you can actually configure an unlimited number of constraints. And for each constraint, it actually contains 8 parameters. And there's many details, however, they are not really documented well. And one plugin can also interact with other plugins, for example, Node Affinity or Node Tent. Each constraint can choose to honor or not honor each of the plugin. So it's pretty complicated for even single controllers. We also summarize more issues in our papers about how the failure can happen from these non-trivial interactions. You can check it out for more details. With all the failure studies, we summarize some properties to verify. The first is called oscillations, as we talk about in the motivating example, that we check whether the system can be in this unending circles of eviction. The system state can change back and forth. The second property is we will check whether the object has been placed into a certain pattern, saying, for example, if you can be evenly spreaded. And the third one is the object number need to fall into a certain range, not being too big that can waste your resources, and not being too less and potentially affect your capacities. And the fourth one is we will check whether the creations, execution or termination of the objects can meet with user expectation. For example, if your pod is still serving traffic, we shouldn't be evicting them. The motivating example is actually violate this constraint. So with all the studies, we propose our system called Kivi, which is the first system for verifying the controllers and their configurations in cluster management system. And we focus on Kubernetes, and it is also an open source project. So comparing with previous literature on the management for these reliabilities, and there are testing and emulations. However, those work are insufficient to handle these dynamic interactions between the controllers in any non-deterministic orders. And comparing between the other verification work on distributed system or networking in particular, those work cannot fit into this new domain of this cluster management because they either focus on low-level implementation details or specific protocols instead of this entanglement of multiple controllers. And also the properties to verify are pretty different in this domain. So let's look into the workflow of Kivi. The users may ask questions is there any oscillations, or is the number of the pod in my system can be more or equal than 10? So with receiving those intents and also the configuration of the cluster, our system have 5 main components. The parser will take into this and parse it into a uniform format we call the cluster setup. That consists we kind of this structure with what are the definition of each type of node, and what are the templates for each type, and what are the configurations saying what are the upper or lower bound of each node maybe in your cluster. It's also including things like intents or event assumptions or the controller configurations. Receiving those, the verifier operator will take generating a profile, maybe contain a subset of the informations, and the model generator is going to pull the models from predefined model templates and then return a model, and the model checker, which we use the existing tool called Spain, that will check for will do the round of verification, and the result will be returned. And the verifier operator will decide whether we need another round of verification, which we'll talk why later, or it will determine that the result is actually ready to be presented to the users. Either we'll reassure user that everything is okay, or we will return a counter example that consists of a sequence of actions that tell you how the things actually go wrong and help user to debug their systems. So let's first look into one of the most important part is the model. How do we do the model? So our main goal here is to verify the interactions between dynamic controller as well as with the event. So with that, like our model will be, we found actually the focusing on the high-level logic instead of the lower-level implementation detail is actually enough to capture the failures caused by these interactions between controller. So with that, we leverage the explicit state model tracking Spain, which is a mature tool that has exists for decades. So what to model in the system? So we need to model the objects, the controllers, and the events. We model each object into this array of attributes and put them into the global system states. And we model these controllers into something called proxy tab, which is provided by Spain. And each controller is implemented as this event-driven loop, and it has this queue that this event queue that in the global system state that can be included by other controllers or events. We also model similarly as for the event, similarly as the proxy tab, so whereby the Spain can check for all the possible interleavings between controllers and events. This two code shows like the example of how we define node and schedulers using Permela language provided by Spain. So here you can see for the node, like this defining what are the attributes and then define them as an array. And then here on schedulers, you can see we define some queues, and in the proxy tab, the main logic will be put into the while loop. So it's kind of like control loop running forever. There are also more modeling details, like how do we model quantities and how do we model time, because Spain doesn't support in time or real integers, real values. So we'll skip them for sake of time. There are also like how do we model the properties, and you can check in more detail in our paper. So in summary here that we implement the 6 mostly commonly used controller and their features. And for each controller, we manually examine the Kubernetes source code, and we capture the most essential details for each controller, and we then further simplify the models by removing some unnecessary data structure. We also omit implementation details like error handlings or like how we handle retries or API calls. So this table summarizes like what are the controllers and events we have implemented and what are the line of code. Okay, so next I want to dive deep into how do we deal with the scalability challenge for Kubernetes. So Kubernetes has this challenge that a cluster can actually reach to hundreds of nodes and even thousands of nodes for machine learning workflow, and you can reach to like thousands of pods in the cluster. So this can bring the known state exploration problem to verification. And there's also this autoscaling and elasticity is one of the key characteristics in Kubernetes. That's saying like the autoscaler may actually change the number of pods or node according to user like resource usage. So there are many topologies user may be interested, like saying this really can be reaching to maybe thousands or really it's really large scale. So with this scalability challenge, we have 2 approaches to tackle it. The first is that we try to optimize on the model from the model perspective, and second, we propose this hypothesis, the verifying cluster at smaller scale. So let's look into each of them. Before we look into about the model optimization, let's firstly briefly mention how Spain works. So it's basically implementing this steps-first search that is starting from looking into its initial states, and it will explore all possible actions, and it will try to store all the visited states, and it will cut the branches whenever you have repeated states, and it will try to find the violations until if we have explored all the possible states. So with understanding this, we really need to reduce the size of global states so that we can reduce the memory usage and avoiding memory swiping when doing the verification. We also need to reduce the concurrencies, and also we need to really reduce the search steps. So for the first one, we try to clearly define a very small set of mutating global variables that we divided all the variables into a stable session and a mutated session, and only this small set of mutated sessions will be tracked by the Spain. And for concurrencies, we merge each control loop into an atomic block. So this is really with the observation that one control loop really takes a really small time, say in milliseconds. So we think it's okay to not checking for the interleavings between this small time frame. And also, we try to serialize multiple controller deployment controller instance. Like this is also with observation that like the failures we sought mostly like within one deployment rather like inter deployment. But like if we do want to check for the failures like between the deployment, we can also disable those features. And to reduce the search depth, we model all the controllers as event-driven loop so that like we can avoid unnecessary search when there is no event happen at all. And for checking for loop properties, instead of like checking for whether the whole global state has been repeatedly happens, we just pick up the key, like partial key variables and check whether those smaller set of key variables has been repeatedly happens to determine whether there is a loop. Okay, so there are like more examples in the paper, just these are some examples. So next, let's look into this hypothesis that we propose that if a cluster can violate an intent, then it can do so at relatively small scales. And this is really because the complexity actually mainly lies in the cluster controller logic and also the configuration that does not really grow up with the scale. So that like all the topologies are generating from this one cluster configuration. So a subset of the topology are often represented enough for all the topologies. So there are also similar observations in other type of distribution systems that other people also have like made published. With this hypothesis, we propose our approach is called incremental scaling algorithm that we start to verify cluster at the smallest possible scales, and we try to increase the scales until we finding violations or reaching empirical sufficient scales. We call it ESC. We further validate our hypothesis, especially for this new domain, to see if it works by examining a collection of real-world failure cases. And this table shows like what are the minimum scales we actually found violations for each case. And the notation here representing like they're saying like 1 node and 3 pod that we found violations for this case. So across all the cases, the max main violation scale is actually 3 nodes and 6 pod, which are not too big. And we also compare this with the reported original report and see what are the comparing between what are the scales has been reported. And in 6 out of the 7 cases, we actually found smaller scales than the reported scales. And we further validate if the smaller scale we found actually can reproduce the same failures in real Kubernetes clusters. So how do we determine this ESC? We can choose this ESC empirically by setting to double of this max main violation scales. In this case, it's the 3 nodes, and in particular, double it will be the ESC can be set into 6 nodes. We also further look into how failure appears against the scales, and this in each of the graph, each dot is representing whether we found the violations on that scales, or if there is no violation on the scales, or if that scale is like just too trivial to verify. For example, the number of nodes is equal to 0, or it's just like pod is too large that the node cannot handle them. So from this 2 graphs, you can see that the violation consistently appear for sufficient large number of node and pod. We also try to fix the number of pod and then like try with like different number of nodes for different type. And you can from this 3 graph you can see the pattern are pretty different. So this really suggests us that exact combination of the number of node and the pod in different type is really matters. And this also suggests us that we need to check for all possible combinations of sizes up to the ESC. So in summarize here for the incremental scaling algorithm, we choose the ESC empirically from the past failures, and we start from verification from the smallest non-trivial scales, and we check for all possible combination of sizes for all types until we found violations, or if we reach to like the ESC. If no violation has been found, then Kivi can conclude that there is no violations with high confidence. Okay, so let's look into the evaluations. We need to answer 4 questions. The first is to validate our hypothesis, which we already talked about. The second is like what is the performance scalability of Kivi and how accurate is Kivi? And can Kivi find new problem in Kubernetes? So this one has been talked about. Let's look into the other three. So the methodology we use here is that we leverage 8 realistic failure cases, and we fill in reasonable details. Then we validate our findings. In particular, the configurations is not really in the original report. We need to confirm our understanding by validate our configurations where real Kubernetes cluster are running. And we expand data set with parameterize the skills because we want to check for whether we can sue for large topologies. And we're also generating a violation or non-violation version because non-violation normally take a longer time for the verification to finish. So for the performance, this graph shows the runtime for Kivi, in particular, how long it takes for running all possible topologies. And you can see that most cases can finish within 100 seconds. And for some cases, you can see it's taking longer time. It's really because there are so many topologies need to be checked, saying thousands of topologies. So that's why it's taking longer time. So we also run some internal tests to see how long it takes for just a single topology, so against a large topologies, like saying hundreds of nodes. And you can see that all the cases has finished within 5 seconds for even hundreds of nodes. And so this really shows our model can perform well at large scales. So how accurate is Kivi? Kivi can find the correct violations for all the violation cases and report no failures for all non-violation cases. And we further compare our verification result with the real Kubernetes logs. In particular, we compare what are the sequence of actions we generated with actual Kubernetes logs about how in the reality how these actions is actually ordered. We compare between them, and this table shows the result where for the cases without any non-deterministic, our matching rate is close to 100%. And for the cases with some non-determinism, we can also be close to 100%. And note here that this result is rather pessimistic. It's really because the Kivi may report a totally valid event sequence. However, due to non-deterministics, it's just not the one really appear in the actual Kubernetes clusters. So this really shows the Kivi can closely model the real systems. We also found 2 new issues in Kubernetes controllers, the logic issues, and we submitted those to the Descheduler GitHub report. So just quickly mention some limitations that we may not scale to the cluster with a large degree of node and pod types. And there also is always going to be a gap between the actual implementations and the models in the accuracy perspective. So I have some more discussions in the paper. You can check it out more for details, and we can also discuss offline. So with that, I conclude my talk, and I'm ready to take more questions. Thank you. Yeah.